or to this computer. There we go. All right, so at the end of last class, we did this little exploration. So we were looking at 3 different graphs that could represent a function f that is increasing, meaning f prime is greater than 0 on some interval. But it was increasing in 3 different ways. So the first graph, remember, which just looks linear, f is increasing at a constant rate, meaning f prime is constant, and therefore f double prime is equal to 0. We talked about that graph having no curvature, meaning it's not concave up or concave down. The second graph, we said that f was increasing at an increasing rate, right? The slopes of the tangent lines were increasing in value. So we were able to say that f prime was increasing and f double prime was positive. And we could see that that graph looks concave up, looks like a cup, right? Concave up looks like a cup. The last graph, the third graph, we said that f was increasing at a decreasing rate, which is weird to think about, right? But what that means is that the slopes of the tangent lines on that interval were decreasing in value, right? We could say that f prime was decreasing. Those slopes were becoming less steep. And f double prime, that means, is less than 0. And the graph is concave down, looks like a frown. So to summarize, f prime tells us how the y values of the graph of f of x are changing. And the derivative of f prime, which is f double prime, tells us how the slopes of f are changing. So our definition of concavity, let f be differentiable on the open interval. The graph of f is concave upward on an interval when f prime is increasing. So that's one way to think about concavity. If f prime is increasing on an interval, that means that f double prime would be positive. So this picture here, this means that f double prime would be positive, greater than 0. And concave downward, if f prime is decreasing on an interval, that means that f double prime would be less than 0. So this is going to lead us to our method for identifying where a function is concave up or concave down. Before we get to that method, here are 4 different types of curved segments that can be drawn. They have different concavity, right, or are increasing or decreasing. So we're going to analyze the signs of f prime and f double prime. And we're going to come back to this later on when we're attempting to determine like what the graph of f looks like given the graph of f prime. We're going to be coming back to this in order to determine what sections of a graph might look like. Simon.
What is this like on the like a numerical line? This is all of those 0 and then on the next one. Always assuming that that middle line is 0. And the 7 is below where the f prime x is below 0.
We're assuming that there wouldn't be any sign changes, like these are just segments. So like we're just going to focus on this first curved segment and determine what the sign of f prime would be and what f double prime would be. So if I were to draw tangent lines to this curve, the tangent lines would have positive or negative slopes?
Positive.
Positive slopes, meaning that f would be increasing or f prime would be positive. F prime would be positive. Now, the slopes look like they are becoming less steep, meaning the values of f prime would be decreasing and f double prime would be less than 0. Sort of. Okay, if we thought about drawing some tangent lines to this curve.
Yes.
Negative sloping tangent lines, therefore f prime would be less than 0. What's happening to the slopes of the tangent lines though? Reading from left to right, what's happening to the values of the slopes of the tangent lines? They are decreasing. They're becoming steeper, but in the negative direction, right? So the actual slopes would be getting smaller and smaller and smaller. Therefore, f double prime would be negative. F prime would be decreasing. Therefore, f double prime would be less than 0. And we just talked about what it means for the graph of a function to be concave down, right? F double prime would be less than 0. To be concave down looks like a frown. Okay, focusing on the curve at the bottom left, thinking about the tangent lines. Positive or negative sloping tangent lines? Negative. So f prime would be less than 0. Are those tangent lines increasing or decreasing in value? Increasing. Increasing. They are negative tangent lines, but they're becoming less steep, so they are actually increasing in value. So f prime would be increasing, meaning that f double prime would be positive. And then the bottom right corner. F prime would be positive because they are positive sloping tangent lines. The slopes of the tangent lines are increasing in value. Therefore, f prime is increasing and f double prime would be positive. And just to go back off of the definition we are looking at above, f double prime is positive, so concave up looks like a cup. No curvature.
So the f.
You find f double prime of a function by taking the derivative of the first derivative.
But like, so for f prime, you know that's greater or less than it's positive or negative slope, and then what, how do you find the if positive or negative?
You're saying, how do we come up with this relationship? Okay. So for this one, the slopes of the tangent lines are decreasing in value,
Oh, okay.
right? Like this is the like, let's say that this is a slope of 3, this is a slope of maybe 1.5, and this is a slope of like 1/2. So the slopes would be decreasing in value, meaning f double prime would be less than 0.
Okay.
Because it's the rate of change of the first derivative. is the second derivative. For this one, the slopes are actually decreasing, they're becoming steeper, but because they are negative slopes, they are decreasing, since they're increasing in the negative direction, which makes them decreasing, right? Like if you thought of this as being like -1/2, -1, -3, right? Those values are getting smaller and smaller. Therefore, f prime would be decreasing, and we would say f double prime would be less than 0. Is that, yeah, okay.
Wait, what is the derivative of certain?
So we can determine where a function is concave up by determining where the second derivative is greater than 0. And we can determine where the graph of a function would be concave down by determining where f double prime would be less than 0. And if f double prime is equal to 0 over an interval, that means that the graph is neither concave up or concave down, but it has to be over an interval. So we're really looking for sign changes in f double prime, which means that we need to identify where potential sign changes would occur for f double prime. So in order to determine those intervals where a function is concave up or concave down, we need to figure out where f double prime would be equal to 0 or where f double prime is undefined, right? Because we're looking for sign changes for f double prime. Does that make sense to everyone? So let's determine where f is concave up or concave down. I wasn't expecting to have done so much quotient rule already today. So sorry, we have another rational function. But we're talking about concavity. So the only thing we need the first derivative for is to help us with finding the second derivative. So let's find the first derivative, use quotient rule, or rewrite it as a product and use product rule if you prefer. But I would use quotient rule here for what you are using the first and second derivative for. So low d high minus high d low all over low low. And just to clean that up, so that'll be negative x squared plus 1 over x squared plus 1 squared. And then moving on to the second derivative. Using more quotient rule. So low d high minus high d low, you have to use chain rule. Don't forget to extend your division bar if you have to. Now, this would be kind of a nightmare to multiply out. You could, but notice that this is a difference of two products, and that there is a common factor of x squared plus 1 in each of those products that also corresponds to the denominator. So to help me simplify, I'm going to factor out x squared plus 1. And then I'll still be left with an x squared plus 1 times negative 2x minus negative x squared plus 1, that'll be times 4x.
Can you just get rid of it in one sec? You have to,
Yeah, if you want to already, I'll write it out, but if you wanted to do that cancellation, you could. This one. And then finishing cleaning up the numerator, so that would be negative 2x cubed minus 2x plus 4x cubed minus 4x. Yep. How are we doing on time? Do you guys know what time we're out of this class? Okay. Doing okay. So the values that we want to identify are where f double prime is equal to 0 or undefined. For equal to 0, if we thought about setting the numerator equal to 0 and factoring, and I can see that would factor right to x minus root 3, x plus root 3. So those values would be 0 and then plus or minus root 3. And there's no real number that would make f double prime undefined, right? There's no real number that would make the denominator 0 in this case, since it's x squared plus 1. So then we can just put those values on the analysis line.
We're always gonna have to use analysis line for this particular, how's that really the same?
Yes, what do you have against analysis lines?
It doesn't matter.
It's technically side work, so you don't have to, but I would. And this is for f double prime, this analysis line. So for test values, we could use -2, -1, 1, 2. When we plug -2 into our second derivative, we get a negative value, which means concave down on that interval looks like a frown. When we plug -1 in, we get a positive value, which indicates concave up, looks like a cup. +1 gives us a negative value for f double prime, which indicates concave down. And then a positive value for x equals to 2. Huh? So we can say that f is concave up on the intervals from -√3 to 0 and √3 to infinity because why? Because Arnav said so.
The slope of f double is
not the slope of f double prime.
The value of that.
Yeah, if anything, it would be the slope of f prime would be positive, but you could say because f double prime, when you've done that analysis line, you want to interpret the analysis line, right? So f double prime would be positive on those intervals. That's why it's concave up, or how you know it's concave up.
This triple prime. Like if you're looking at a Q function and it has triple prime and.
The AP Physics, what does f triple prime tell you about, like, if motion? Not the acceleration, f double prime would be acceleration. The rate of change of the acceleration, which is known as the, I just learned this year. If acceleration is changing, it's called the jerk. The jerk.
And you're in, that's a terrible name.
Okay, concave down, that's the only interpretation of the third derivative that I've ever heard. And that's the only, so that's the only reference. I've never, in a calculus class, I don't recall ever using the third derivative. Right. No. All right, concave down from negative infinity to negative √3 and 0 to √3 because
Consider that the
That's when you get the.
that's whenever it changes concavity. Which leads us, thank you, Simon, for that transition, which leads us to, what do we call those points where concavity changes? Points of inflection. Points of inflection. Now, here's what's interesting. Different texts have different definitions. If you get into the nitty-gritty of the definition of a point of inflection, different textbooks have different definitions. Now, in general, points of inflection occur where concavity changes. But what if you have a point, like a graph that has something like this?
Ooh.
That's not.
Down to concave up. Would this be a point of inflection?
Yeah.
No.
Our textbook says no, some say yes. Textbook says that for a point to be a point of inflection, it has to have a tangent line. So either a positive or a negative sloping tangent line, a horizontal tangent line, or a vertical tangent line. Some texts don't have that requirement yet. I put that on there. Some texts don't. See, because it is controversial, in this class we'll stick with our textbook, but because it is controversial, it's not going to come up.
Oh. Only everything you have nothing.
There's infinitely many tangent lines you could draw at that point. So, well, it is a point that you would have to consider. The second derivative wouldn't exist there. Like, it would be a point that you would put on the analysis line and concavity changes, but our textbook would not consider that to be a point of inflection. I don't know what I think.
I think.
Concavity changes, so some people would just right away tell you point of inflection. But but based on our text, it's a no. No,
So it's actually where the F double prime goes from positive to negative to positive.
yes.
That point does not have to exist according to some textbooks, and the point has to exist. according to-
Well, no. It has, so the function has to be continuous, just because the function is continuous doesn't mean that F double prime or F prime exists there.
Yeah, that's what I'm saying, like F double prime, I have a whole, but it turns from negative to positive. What's that?
Right, you're right, so F prime, but a vertical tangent line, like you could have a vertical tangent line, and F prime and F double prime wouldn't exist at that point.
So that, the third example is not like the reflection.
It is. But that's not a vertical tangent. line. This would be a vertical tangent line, that would not be. That would be no tangent. Or infinitely many.
So then how does that count as a point of inflection according to our?
Vertical tangent,
But F double.
right, but that doesn't indicate. So in this case, the slope.
Oh, they're saying the tangent line has to.
For
Oh,
zero.
I see. Okay, that's weird. So.
You guys, you don't have to stress about it too much. I just think it's like an interesting thing. Like it's like, if you go into like math stack exchange, like there's like pages of arguments for whether or not a cusp would be a point of inflection or not. So identifying, we don't have a name like critical number. Some texts I have seen, but not very many, have referred to the values where F double prime is 0 or undefined as being like hypercritical values. We're just going to refer to them as possible points of inflection. So we're going to determine the points of inflection and discuss the concavity of H of X.
Super trooper inflection. So usually about H from X, and H double prime.
We do. So what that would be 15x to the fourth minus 15x squared. So H double prime would be 60x cubed minus 30x squared. H of X is a polynomial. Oh, thank you. So its first derivative and its second derivative are also polynomial functions. And we just need to figure out where H double prime would be 0. So factoring out 30x. Okay. So our possible points of inflection . PPOI, your PPOIs. Poise would be at 0 and then plus or minus √2/2. And then Simon's favorite, doing the analysis line.
Yeah.
I think it sounds like it's in the gym.
Wait, what closest to the?
I don't know, but we gotta finish this, so let's stay focused. Okay, so putting our possible points of inflection on the analysis line, plugging your test values into H double prime, this analysis line is for H double prime, we would get negative, so concave down, to positive, concave up, negative, concave down, positive, concave up.
Oh. Looks like. It's really close.
So first, in discussing concavity, here, I'll do this in two separate steps. Concavity. Concavity, we could say concave up looks like a cup from -√2/2 to 0. And from √2/2 to infinity. Because
Double prime of X.
is greater than 0.
good. And concave down, not or equal to.
No, yes, wait, the way that I said it.
That's fine. I don't mind abbreviations. Just no abbreviations. Don't use abbreviations on your actual exam. Because concave down, because
I knew it. I believe I remember that person's name. I don't remember the Tom's name.
H double prime is less than 0, good. And then let's talk points of inflection. So points of inflection occur where there's a sign change in F double prime. We do want to be specific though. Notice that at -√2/2 and √2/2, H double prime changes from negative to positive. So I'm going to lump those together. So points of inflection at X equals to -√2/2 and X equals to √2/2 because H double prime changes from negative to positive at these values, or you could just restate at X equals -√2/2. They're the same type of.
Could you just say that they change signs?
I think you could, but it's safer to be more specific. I'm getting there. And then there's also a point of inflection at X equals to 0 because H double prime changes from positive to negative. Okay, so this is where our quiz will stop. Quiz stopping point. Quiz stop. Your homework will have some second derivative tests. We are going to keep talking about second derivative tests, but I'm telling you, your quiz will go through determining possible points of inflection, and concavity, concave up versus concave down. Arjun. Yes, I'm doing that for all of my classes this year. I think that it's helping.
I think so. It's
Yeah?
like less stressful. He's always complaining when you give to them. You're more prepared.
I've done it for every quiz and test.
He's like a little ungrateful. I don't feel it's so late.
You guys, I'm sorry. I have small kids and sometimes I'm not able to sit down and write the test until after 7 o'clock.
Infinitely more time on your part than some of the teachers that I. Well, there is one teacher who was named whose course is 11 years old.
All right, you guys.
And Alex could convert.
Second derivative test. Now, you guys already have in your toolbox the first derivative test for identifying local and relative extrema, right? The second derivative test will come up. And it's not foolproof. It's kind of like when it can be applied, or you'll sometimes have to interpret that given information is using second derivative test. But if you have a function such that f prime of c is equal to 0, isn't that one of the cases for a critical number? Right, where c would be the critical number. Maybe I shouldn't use the whole. C would be a critical number, but it's only one of the cases for a critical number, right? Because critical numbers can also be where f prime is undefined. But in the case that you have a critical number that causes your first derivative to be equal to 0, and the second derivative exists on the open interval containing c, if f double prime of c is positive, if f double prime of c is positive, where are you guys looking at? Oh my God. If f double prime of c is positive, that means that c is a local min. So let me give you a visual for that. If f double prime is positive on an interval, that means that f is, if f double prime is positive.
Oh, changing and increasing.
Which would mean that it is concave up. If f double prime is positive, concave up, which means if you have a point, stop talking while I'm talking. If you have a point c comma f of c that corresponds to a horizontal tangent line, that point will also correspond to a relative minimum.
Wait, maybe about future, but can we do the opposite of the derivative?
You're thinking about next semester. Hey, if f double prime is a negative on the interval that a critical value from horizontal tangent line lies. So f double prime negative means concave down. So if you have a critical number such that there is a horizontal tangent line, c comma f of c, then that is a relative max. The thing is, if f double prime of c equals to 0, it's inconclusive. Could be a relative max, could be a relative min. You need to go back to your first derivative to determine. Why can't we consider critical numbers where the first derivative is undefined? Like, why can't we consider those values in our second derivative test? Are you doing this? Are you raising your hand or doing, I don't know. He doesn't know.
He doesn't know.
He doesn't know. Okay. If your first derivative is undefined at a value, will your second derivative be defined there? No. Which means you can't evaluate your second derivative for that critical number. That critical number could still correspond to a local max or min, but the second derivative test is not a way of determining whether it is a max or min, local max or min. How much time do we have?
2 minutes. If you wanted to make it 40.
It's probably 46 and 51 minus 46 is.
Oh, yeah, and that 42.
We're just gonna spend the next 2 minutes talking about that. So I'm gonna stop here. Your homework, so I'm telling you, your homework, I think, has some second derivative test problems on it. Look at them, see if you can figure it out, but we will pick back up with second derivative test on Thursday. Your quiz is the beginning of class on Thursday on 3.1 through points of inflection. I will send out information, and then Friday we will wrap up 3.4. I'm going to give you an optional assignment for the Thanksgiving break on 3.4. I'll think about it. And then I'm also going to give you guys a really easy lesson video to watch over the for your downtime.